Okay, so there's another thing we need to talk about briefly for the deciding whether something is aromatic or not, and that is ions. So we know that benzene is aromatic, and benzene is not an ion. It's neutral, but it satisfies the four requirements for something to be aromatic. It's a ring, it's planar, it has a conjugated pi system, and it obeys Huckel's rule because it's got 4n plus 2 electrons or an odd number of pairs of pi electrons. So as it turns out, we can apply that to ions as well. So let's take the cyclopentadienyl anion. So this is cyclopentadiene just deprotonated by like a base or something. And so we do have a conjugated pi system because we can draw a resonance structure where, for example, this lone pair comes down here, and the double bond goes on to that carbon atom. Lone pair there. So we can draw resonance structures, so that is a conjugated system. And then if we count the number of pi electrons, well, this lone pair is involved in the conjugated pi system, and so they are pi electrons. And so we've got 2, 4, 6 pi electrons, which is good because that is that satisfies Huckel's rule. We can use the same logic for this 7-membered ring with a positive charge, tropylium, this is called, and we can also draw a resonance structure where this positive charge is involved in the aromatic system, or the system that we think is aromatic. So there, and a positive charge there. So we know that that positive charge is involved in the conjugated pi system. Now, there's no lone pair where that positive charge is. But that's okay because we already have 2, 4, 6 pi electrons in the system. If we had a lone pair there, then we would have too many electrons, and that would be anti-aromatic. But because we only have 6 pi electrons, that satisfies Huckel's rule, and these are both aromatic. Okay, so all of the compounds, the aromatic compounds we've talked about so far, have just had carbon in the aromatic ring, but that doesn't necessarily have to be the case. So we can have heterocyclic compounds, hetero meaning different, and so we've got an atom that's other than carbon in the ring, and these are actually fairly common. So If you replace one of the CH groups with a nitrogen, you get pyridine. Five-membered ring with a nitrogen, that's pyrrole. With oxygen is furan, sulfur, thiophene, and then there's some other interesting ones. This particular one has a fused ring. That's indole. So all of these are aromatic, but you'll notice, particularly with the two here that have nitrogen, that they look different. And I mean that by this nitrogen has a double bond, and it in this case it looks more like benzene, right? Just like nitrogen benzene. But for this one, you see the carbon-carbon double bonds, and those look reasonable for an aromatic system. But the nitrogen doesn't have a double bond to it, and it turns out that in this case, we're going to use the lone pair to participate in aromaticity. So let's look at that in some more detail. So in pyridine, the lone pair is not involved in aromaticity or in resonance structures, and we call that localized. So if we treat pyridine like benzene, and we draw a resonance structure like that, let's see, now have this. And we've managed to draw a valid resonance structure. However, the lone pairs have not done anything. They're still sitting on top of the nitrogen atom. And that's what we mean by they're not involved in aromaticity, and they're localized. So they are local to the nitrogen atom, they just stay there. They don't react in terms of aromaticity, but because of that, because they're not involved in aromaticity, they can be used to pick up a proton. And so pyridine is basic at that nitrogen atom. However, in pyrrole, those electrons in the lone pair do participate in aromaticity, so we call them delocalized. So what does that look like? Okay, so there's our lone pair. And if we draw a resonance structure, let's see, what shall we do? Let's have the lone pair go down and make a double bond, and we'll have this pi bond come and sit on that carbon. There's several different things you can do with this molecule, but that's one of the possible resonance structures, and it illustrates this pretty well. So we've still got the same connectivity of atoms. We've moved those electrons down to make a double bond there, and these pi electrons are now sitting as a lone pair in that carbon atom. So that carbon has a negative charge. We've still got our pi bond over there, and nitrogen now has 4 bonds, and so it has a formal positive charge. So you can draw other resonance structures where you have a further movement of electrons around the ring, but the important thing here is that in at least one, and in fact in pretty much all the other resonance structures of pyrrole, except the way you normally draw it, the nitrogen has a positive charge and it doesn't have a lone pair. So because that lone pair on the nitrogen is not really there all the time, it's delocalized, and so that actually changes the reactivity of pyrrole. Pyrrole is not basic at that nitrogen atom because the lone pair is too busy doing resonance stuff and doesn't have time to take up a proton. Now, if you try to do this sort of thing with pyridine, where you try and take the lone pair and move it into the ring, you're going to end up with one atom, probably a carbon atom, having more than an octet, which is illegal. And so that is sort of a cushion for you if you say, okay, let me try and figure out if that lone pair is localized or delocalized. If you try to draw a resonance structure and you can't do it because there's too many electrons, they're crashing into each other, they're causing carbons to have more than 8 electrons, then you know that that lone pair needs to stay up on top of that atom and not move into the ring. The other way you can look at it is, all right, in all of these examples, from pyrrole over to the right, there's no pi bond to the heteroatoms. All the pi bonds are carbon-carbon bonds. And in all of these, the lone pair is delocalized. So if your heteroatom only has single bonds, then the lone pair is delocalized. But, like in pyridine, you have a carbon-nitrogen double bond. In effect, that's saying, okay, the pi electrons associated with that nitrogen are in the double bond, not in the lone pair. And so if you've got a double bond like that, those are going to be localized electrons and they're not going to participate in aromaticity. Okay, let's talk about a few reactions of aromatic compounds. First, we're going to talk about reactions at the benzylic position. So the benzylic position just means that you're right next to the aromatic ring. So this methyl group here, that's a benzylic position. The CH2 of this ethyl group is a benzylic position. Let's say you've got a carbonyl or something there. Then that carbon, because it's attached to the benzene ring, but not part of the benzene ring, is also a benzylic position. So we can oxidize the carbon that's at that position. For example, if we take butyl benzene and we treat it with chromic acid, or KMNO4, potassium permanganate. Those are both really strong, really harsh oxidizing agents. And in fact, they're so strong that they will basically slice off the alkyl group and just leave a single benzylic carbon right there that is fully oxidized to the carboxylic acid. So we've actually lost 3 carbons. They've just been torn away by the very strong oxidizing agent. And we get a carboxylic acid. Yes?
So for the alkene segment, does it matter like how long the alkene is?
The alkane?
Alkane, yeah. Sorry.
No.
Like if it was like, what's that? 6
If you
months,
right, and if you had, let's say you have some giant molecule over here on the side, it's still going to cut that off, which is says less about the aromatic system and more about that you shouldn't let these chemicals touch your molecule that you've been working very hard to synthesize. Fortunately, there's a lot of nicer reagents to use, but yeah, chromic acid and permanganate are very harsh reagents. So in order for that reaction to occur, we have to have essentially space at the benzylic carbon to oxidize. And so if the benzylic position is quaternary, and we try to do an oxidation, that's what the ox means, with whatever reagent, we will not get anything. So that could be a good way to protect that carbon from being destroyed by some harsh reagent is if it's quaternary, it's got 4 bonds to it that aren't hydrogen, then you're not going to get a reaction at that position. Okay, this and really some of the following things are based on the fact that the benzylic position right next to an aromatic ring, when there's reactions of some sort happening there, the transition states or the intermediates or whatever are often stabilized by resonance because it's next to the aromatic ring. So if you've got a molecule like this, and you treat it with bromine and some sort of light to initiate the reaction. That's what H nu means. We will get pretty selective bromination at the benzylic position. Yes.
You said HU, is that an HR or an actual HB?
That is, it's the Greek letter nu. It's like a V. You can write HV, and it's okay. That just means light. Usually it's ultraviolet, but kind of depends on the specific reaction. Okay, so if we kind of go back to organic chemistry 1 and think about SN1, SN2, E1, E2, all of those fun reactions. Fortunately, we can do those pretty easily at benzylic positions. And so, let's see, SN1, SN2, E1, and so all of these reactions work. And I'll go ahead and draw out some examples. SN1. There's an SN2. Got to have a less hindered carbon atom there for the SN2 to occur. can do elimination reactions as well. And elimination reactions are especially favorable at, no, that's wrong. Should be a hydrogen there. Elimination reactions are especially favorable at the benzylic position because the product is resonance stabilized with the aromatic ring. So that's part of the whole conjugated system there. So
Just to clarify,
yes,
if the H2SO4, what was the name of that?
H2SO4,
E.
sulfuric acid.
Oh, I went I just read this one. I thought it was a thing from before with the CR.
Oh yeah,
And
yeah,
I actually looked at it. Never mind.
Okay, how are we on? Not necessarily on those reactions, but just the fact that you can do them easily at benzylic positions. Okay. There. No, it's okay.
So what's the difference between the E1 and the E2?
Just the mechanism. So this one is the reagent used as acid, and here it's a base. But in this particular case, you get the same products for both of them. Okay, so we might have an aromatic ring and we need to get rid of the aromaticity. Yes?
Real quick, I'm sorry. What's the difference between E1 and E2?
Just the mechanism.
Just the mechanism.
Just the mechanism. One of them is with acid and the other's with base, but you get the same product.
Sweet.
Yep. If we need to just hydrogenate benzene, you can do that. You can put it in a reaction vessel with hydrogen gas, a nickel catalyst, but the problem is you have to heat it up to 150 or something degrees Celsius, and you have to do it at very high pressure, 100 atmospheres, which is kind of ridiculous. This is not a practical reaction to do in the lab or even in industry, because if you actually just want cyclohexane, there's plenty of other better ways to get that from petroleum and such, but you can do that reaction. What might be a better thing to do is, instead of hydrogenating the actual aromatic ring, you can take something that has an alkene that's not aromatic. In this case, it's conjugated to the aromatic system, but it is not aromatic. And now you can use a lot milder conditions, room temperature, and only 2 atmospheres of pressure. And you will keep the aromatic ring, but what's going to happen to the alkene? It's going to get hydrogenated. So this is useful. You've got a method to hydrogenate alkenes in the presence.
The catalyst, right?
Catalytic, yeah, some sort of fancy palladium catalyst. I can draw one out for you if you really like, but just suffice it to say that you throw some metal with some stuff in there and it works. So that's nice. We can hydrogenate alkene in the presence of an aromatic ring. Much more useful than just cooking something at 100 atmospheres. Anything that has 100 atmospheres of pressure in it is called a bomb. And so you don't want to be doing that in the laboratory, or really on an industrial scale either. Okay. Yes. This is PD, palladium. It still looks like POL. Sorry, palladium. Okay, so if you recall from OChem 1, if you don't, it's okay, because we're going to talk about it. Alkynes can be reduced by a dissolving metal reduction. Okay, what does that mean? So we can take an alkyne like that, and if we treat it with sodium metal dissolved in liquid ammonia, not aqueous ammonia, but actual anhydrous liquid ammonia that has to be done at minus 50 degrees or something like that, because ammonia is normally a gas. We can partially hydrogenate or partially reduce the alkyne to an alkene. Now, what does that have to do with benzene? Well, we can kind of do the same thing to benzene. So, let's take benzene and treat it with sodium in liquid ammonia. And we get a very interesting product. we get that, which is 1,4-cyclohexadiene. Now, is that aromatic? No. Does that even have a conjugated pi system? No. So we've completely gotten rid of any sort of conjugation going on because we've got 2 hydrogens on that carbon and 2 hydrogens on that carbon. And we've created 2 separate alkenes. And now in this example, the molecule is symmetrical, but if we had stuff attached to the benzene ring that ends up being attached to the products, then we can treat one double bond maybe with some reagent and do a reaction on that side of the molecule, and then treat the other double bond with some other reagent, and so we can do a lot of chemistry based on that. But we completely remove aromaticity and conjugation in that reaction. Now that's just for benzene itself. But if you have a substituent, like an alkyl group, then the preference of this reaction is for the carbon that group is on to not get that extra hydrogen atom. Okay, so what does that look like? Well, let's take toluene. And do that same reaction. The product that we actually get is that, as opposed to that. So what I mean by its aromatic carbon is not reduced is that this carbon atom has no hydrogens on it in the starting material. In the product, the one that's actually formed, that carbon also has no hydrogens. For this product that does not form, we do now have a hydrogen on that carbon. And so in this case, reduction means adding hydrogens. Questions on the Birch reduction? Okay, that's all of chapter 17. So let's, hello. Oh. That's literally what I was going to bring up. You're welcome. Okay, so let's do a couple of these. Let's do L. Let's do KLMN.
So you have the
KLMN, all in a row.
Could it just be P? It doesn't have to be the 12.
Yes. Okay, so K. I, J, and K are all xylene, which is dimethylbenzene. But which isomer is K? Is that ortho, meta, or para? Yeah, that's meta. So you could call it, probably the best name would be metaxylene. You could call it meta-dimethylbenzene if you wanted to. You could also call it 1,3. Dimethylbenzene. But metaxylene is the best name for that.
How is K meta and not ortho?
So ortho would be like that,
Okay.
or like that. For meta, there's always one carbon in between the two
Okay.
substituents.
Okay.
Yeah, yeah. Okay. L has two sort of equally correct names. Anybody want to give it a shot? Yep. So we have two possible parents, or like parent molecules that we can use here. We can say that the parent is methylbenzene or toluene. Or we could say that the parent is this, which is aniline. So let's say that we want the parent to be aniline. So that means that our reference group is right here. And so this methyl group is right on the next carbon, so that's ortho. So that means ortho, and we're referring to the methyl group. So ortho-methyl aniline. Or we could say, okay, let's have the parent group be toluene. What is this thing? Anyway, so we could say that the parent group is toluene, and the NH2 group is 1 over, so that's also ortho. Not a coincidence that it's ortho in both instances. And the name of the NH2 group is amino. So ortho amino toluene. For M, are we going to use orthometaphora? Well, we've got 3 substituents. So we can't use orthometaphora, and we have to use numbering for this one. And so, got that oxygen atom. You've got this benzene with an alcohol. That's phenol. This carbon is going to be the number 1 carbon. Normally we would have to figure out which group is higher priority to figure out which way to do the numbering, but fortunately this is symmetrical. So we've got methyl groups on the 3 and 5 positions. So that means we get 3, 5. Dimethyl phenol. What should our parent molecule be for N? That's benzoic acid. And we've got a chlorine at what position? Ortho. So this is ortho chloro benzoic acid. Yes. Yeah, yes. So the parent is going to be, well, you could say that the parent is toluene because you have methyl groups, but probably the best thing to do here would be to say that the thing with the heteroatom is the parent chain. So this is phenol. We number the carbons 1, 2, 3, 4, 5, 6. And then the substituents are just those two methyl groups at the top. And based on the numbering, in fact, it doesn't matter if you number clockwise or counterclockwise. The methyl groups are at the 3 and the 5 position. So you put those numbers here, and then dimethyl in the parent chain. Yeah. Okay, let's do E, F, G, I, J, K. All right, so E, F, and G, those clearly kind of go together, and I, J, and K also look very similar.
I think so. I also
plus 2. So if you have an odd like plus 14, that's yeah. So 4 times is 18 plus 2 is 18.
I'm assuming which it should have.
So 8 is enough. You have to make it equal. So if you have 4 practicals and you 4 times 1, right? 4 times 0 is equal to 2, right? Plus 2. It is not 4 times 1 is 2. It does not because it doesn't equal. It's not times plus 1 plus 2 equal your number. You can do it for
But we just like what if this was
So this double bond is isolated. So if you hydrogenate this one, it's easier. And hydrogenate that one. It's not. Just go like this. Yep. It's just based on this stuff is just based on the reagents. It's going to be a clue to what. So
all three of these okay?
it's not the same because this whole molecule is rings aromatic. And so that's not going to touch either of those double bonds. There's no reason.
No, because even the first one would be aromatic. This one, if it passes,
Okay, so the ones at the top with no charges, what are those? These are both non-aromatic. And the easiest way to tell is because we've got 2 hydrogens up here in both cases, and that prevents them from being, the rings from being fully conjugated around all the carbon atoms. So that's an automatic fail for those 2. Okay, so the positive and negative charges. On the positive charges, we've got, I'm going to put them back, hang on, don't worry. On the positive charges, we've got 1 hydrogen atom, and we don't have any lone pair on the carbon there. On the negative charges, we also have a hydrogen, but that carbon atom has a lone pair in both cases. Okay, so all 4 of these are conjugated pi systems, right? So this double bond can be moved up here, and we can put a positive charge there, so we can draw resonance structures where all of the electrons move around the ring. This one looks a little uglier because it's small, but you can do a resonance structure where it moves around the ring. So that's conjugated. I know it's small, but I'm just gonna write something else there. So you can do that resonance structure. You can also draw resonance structures for both of those with the negative charges, where the lone pair on the carbon atom moves throughout the ring. So those are conjugate, so those pass the third rule. Now, the only thing left is Huckel's rule. So, F, let's see, F, G, J, K. Okay, so F, what about Huckel's rule for F? It's got 2 pi bonds, and that's all the electrons in the pi system. So does it pass or fail Huckel's rule? Fail, so it is anti-aromatic. G, how many pi electrons do we have in the system? We've got 2 pi bonds, and we've got that lone pair that can participate in resonance structures too. So we've got 6. Does that pass or fail Huckel's rule? Pass. So this is, yep, this is aromatic. J, how many pi electrons does J have? It's got 1 pi bond, and there's nothing up on that carbon, so it's only got 2 pi electrons. Does that pass or fail Huckel's rule? Yeah, 4n plus 2. If n equals 0, then you get 2. So that does pass Huckel's rule. And so this, as weird and as cursed as it looks, is actually aromatic. If you have an odd number of pairs of pi electrons, it's aromatic. And what is an odd number? Yes? Yep. So the number of pi bonds is 1, and then the number of lone pairs is 0. For this molecule, like there's no lone pair anywhere, we've just got 1 pi bond. So total pi electrons is 2. Huckel's rule states that you need 4n plus 2 pi electrons for something to be aromatic. We have 2 pi electrons. So we need 2 to agree with something 4n plus 2. And we can do that if n equals 0. Or you can say that we've only got 1 pi bond and no lone pairs. So that's an odd number of pi bonds or lone pairs total. And that satisfies Huckel's rule. So it's aromatic. Okay. What about K in that case? Yep. Because now we have 1 pi bond and 1 lone pair in the conjugated pi system. And that's 4 pi electrons, which does not satisfy Huckel's rule. Or you could say, okay, there's 2 pairs of pi electrons. 2 is an even number, and so that fails Huckel's rule. So it's anti-ring.
I have a question.
Yes.
You probably already answered it, but for the whole first line.
Yeah.
Those are not planar, correct?
Correct.
Or- okay, and that's why they're not, because of the two hydrogens coming out the top.
Yes, but the other main thing is that this carbon is not conjugated
Okay,
to the rest of the. So this is a conjugated system down here, but the whole ring has to be
okay.
a continuous ring of conjugated.
Okay, I can understand.
Yes.
Good question. I've already said this, but how do you know when they're planar and
It's pretty hard, and so I'm not going to give you any examples of things that are not aromatic only because they aren't planar. So, trying to think of an example. Really the only example, I don't know if did I talk about it? Maybe I did not talk about this, but no, I didn't actually.
I don't get it, I'm sorry.
Okay, that molecule,
Okay. I got you.
which is a ring, has a conjugated pi system and has an odd number of pi bonds, so it passes Huckel's rule. That should be aromatic, right? It's not, because close your ears if you don't want to worry about this, but there's hydrogen atoms here that are crashing into each other and it causes the ring to warp. But I would not give you that example. So don't worry about it. Okay,
can we do the last three?
the last three on this? Yes. What is that? FGH. Okay. Three, last page. Okay, for F, what reaction, just based on that brief overview I gave you, what reaction uses sodium ethoxide or sodium methoxide? Yeah, that's an E2. Let's see. So this is going to be an E2 reaction. So we need to do an elimination. Now, I think it's fairly clear that the bromine is going to be involved with that elimination. But there's also a hydrogen that's going to go away. We're going to eliminate HBr. So where is that hydrogen going to come from? The back. Like this one? Nope. Because those are both, that hydrogen and the bromine are both on the same carbon.
Well, it comes from the natural group.
Can we take the hydrogen from there? Why? There's no hydrogen there. But there's three hydrogens here, so we can take one of those hydrogens and make that.
Wait,
Yes,
why wouldn't it come from that central carbon?
this one, because then you would, so this bromine and the hydrogen are both attached to the same carbon,
Oh, okay.
and you've got to have two adjacent carbons because you have to form a double bond between two carbons. G, what sort of reaction is this? Sodium and liquid ammonia.
Okay, and you need the
It's the very last thing we talked about. Birch reduction. So, methanol is just a solvent here. So we have two possible products that we could get. We could have the that, or, yes, that was correct. This, A or B, which one are we gonna make? B. So this is not, this carbon has been reduced, and we don't want to do that. And so,
For B, just like in theory, make a C and just put the lines going the other way, or no? Like instead of them being on this side, put it on the opposite side.
yes. Or, you could do that, that's the same model. H. We're taking, what is this? Got these two ethyl groups. And we're adding chromic acid. So what does chromic acid do to those alkyl groups? Yep, so all we're going to do is tear them off and replace. We are going to end up removing a carbon from each one, but that's okay. And we're going to have a dicarboxylic acid like that. Okay, thank you very much. We'll start chapter 18 next time. Talking about drawing the starting material. It's the same thing. Get ready for the next packet. Get ready for the next one.